Hello everyone. Today my team and me gonna present on the video on the integrator, differentiator, and op-amp adder circuits. Basically, I just explained the structure of IC, the IC how it looks and how it functions. Here you can see the inverting input at pin 2 and 3 is a non-inverting input, and pin 7 and 4 are the power supplies, and 6 is the output. And offset, the pin 1 and 5 are the offset nulls, which are optional. We are not using them here. Yeah. And this is how the integrated circuit looks like. We have Vin here and resistor, and the feedback of capacitor is attached here, and the two power supplies 12 volt and 12 volt. And the non-inverting pin is connected.
Hello, my name is Gurgal Meena and I am going to explain integrator circuit. Here we supply 12 volt power and this is our common ground, this is our positive power supply, this is our negative power supply. Here we take an input and this is our output, and this is our 1 kilo ohm resistor and this is our 100 nanofarad capacitor, and this is IC.
The output of this integrator circuit. Here we can see the input is a square wave 2 kilohertz, and we can see the triangular output here.
Now we replace 1 kilo ohm resistor to 2.7 kilo ohm resistor and everything is same.
This is the data and graph of integrated circuit of 1 kilo ohm resistor. Here we have calculated the 20 log V0 by Vi. Here the graph is of 20 log V0 by Vi versus frequency. Here we have changed the frequency from 100 to 100 till 10,000, and we have maintained the input voltage constant as 1000. Here the output voltage is 5080 to 220 as it is decreasing, and the 20 log V0 by Vi was we have got the values like this. Here we have positive points till certain point, and then the values are negative. Here we can see the graph is in decreasing posture actually, and this is the data and graph of integrator circuit using 2.7 kilo ohm resistor. Here we have calculated the 20 log V output by V input, and here also we can see the graph which is 20 log V output by V input versus frequency. Here we have changed the frequency 100, 125 until 3000. We have maintained the input voltage in constant, which is 1000, and V output is 6000, 4800 until 400 it is decreasing. We have got results like this. 20 log V0 by V input is positive till certain point, and here also we can see the negative values for certain values of frequencies. Here this is also a decreasing posture of a graph.
We are going to explain about differentiator circuit. In this circuit we just swap the capacitor and resistor, and now the graph, this is our input graph and this is our output graph. This is our specs and this is square. First we took the 2.7 kilo ohm resistor, now we took 1.7 kilo ohm resistor, and this is the graph.
Hello, I'm Kirti. It's a differentiator circuit of 1 kilo ohm resistor, and here we are giving sine wave as input. As the differentiation of sine is cos, here we are getting the output as cos. The yellow one is the output and the blue one is the input sine wave.
So this is the data and graph of differentiator circuit using 1 kilo ohm resistor. Here we can see the graph which is gain versus frequency. We have calculated the gain actually here. Here we can see the frequency. We have changed it from 100 to till 2000, and the V input is constant, which is 1 volt, and the V output is increasing gradually. We can see here from 160 to 760, and we have got the gain values in minus at negative, and we can see the graph is in increasing posture, and from the 1000 the graph has become saturated like this. We can see the horizontal straight line. And this is the data and graph of differentiator circuit using 2.7 kilo ohm resistor. Here we have plotted the graph between gain and frequency. we have changed the frequency from 100 to 4000 as we can see here, and the input voltage we have given is constant, which is 1 volt. Here the V output we have got is increasing, that is from 180 to 1460, and the gain we have got is negative till 1500 frequency, and then we are getting positive from 1500 frequency. Here we can see the increasing posture of graph, which looks like this.
Today I'm going to explain the adder circuit. Here we have two inputs. Input number 1, which is 1 VPP and 1 kilohertz. It's a sine wave, and other one is also sine wave. Input number 2, 0.5 VPP and 3 kilohertz. These both are connected in a parallel by 20 kilo ohm ka resistors, and then this IC has a feedback of 10 kilo ohm resistors, and this is our positive power supply, which is connected to the 7th pin, and this is our negative power supply, this blue wire, which is connected to the 4th pin, and ground 3, the non-inverting pin is connected to the ground, and this is our common ground. You can see here all grounds are connected to this common wire. And now the output of this wire is connected by here's the 6th pin, and is connected by the blue wire here. Here you can see as it is a inverting amplifier, so the whatever output we are getting, it is inverted, so we need to invert once again to get the positive output. So we are second IC we have a buffer amplifier here. Now the output of the first amplifier is connected via blue wire, and now it is connected to the 1 kilo ohm ka resistor, and this buffer is feedback with the 1 kilo ohm resistor. And you can see here the power supply, this is 4th pin. The negative power supply is taken by the power supply of the first, and same with the second one. Positive power supply is taken from the first amplifier. And here we can see here the output, the 6th pin, the output is connected to the oscilloscope here. Okay, let's see the graph in the oscilloscope. Here we have our power supply. We are supplying a voltage of 12 volts. This is our signal generator, where we have where signal 2 is 3 kilo and 5 VPP, and signal 1 is 1 kilohertz and 1 VPP. Now we are moving on the oscilloscope. Our final output, which is the average of two input signals. Here we get an approximate peak to peak output voltage of 500 millivolts and a phase difference of approximately 0 degree, which shows that the input and output are in the phase with each other. Now let's take a look at our FFT to understand what are the constituent frequency in our output waveform. So here we have our cursor. I'm moving it on our first peak that we see, and we observe that it's approximately 1 kilohertz. Now moving it to the second peak that we see that it comes at approximately 3 kilohertz, which shows us that the constituent input signals had 1 kilohertz and 3 kilohertz respectively.